guys.
Set
Okay.
the RP. Set RP. The first one.
On this. Oh yeah, correct. Congratulations, you remember.
He just told me the RP is the rapid prototype.
No, not me. He said.
Okay, no problem. It's okay for you because you don't know. So you can be wrong. So here I will just make another RP.
Okay, made another RP.
Yeah, it's a very rapid process. So you just select and click.
On the center?
Yeah, on the center. Because we need to take the data from here. The impactor will land on this one.
Yeah.
It's a really important point. So now we have done this. We set the
Only
surface.
top face or top face?
Only the top face.
Okay, top
Yeah.
face.
Another thing is we have the impactor, so we did not set the surface for this. So now we have this. We'll make the surface for the impactor also.
But it's a curve.
Yeah, the curve can be a surface also.
Okay.
反正就是会接触到的面都要设一个
对
surface.
Right?
Yeah.
Because I can understand you are giving some information.
Yeah. You understand he's giving some, but you're not sure he's giving the right or wrong.
It's like World War II.
Yeah.
They know there's information, but no one knows what's the code.
Yeah.
So if I say the, then he thinks that I know Chinese, but I don't know anything.
Yeah, you didn't get his name.
So I select this front surface and this cylinder part because this when the punch goes down, this part and this will
touch the because it was inside the
because the sample becomes like this, right?
You will wrap it.
Yeah. So we don't select this because it's of no use. This is totally long like this. So this is just a prototype for that. And click on done. So now we have the impactor surface also. So we are all set. We created all the surfaces. Okay. Let's go to the property menu. In the property menu, we need to first define the materials. So you see this graph, create a material. Click on create, then we come to this window. So in our case, we have TPU. So I just write TPU, and the TPU density is around 1.23 gram per centimeter cube. But in Abaqus, you need to follow the units because Abaqus does not have units. So always take a reference. You see, this is the unit table. So usually we follow the SI unit system, in which the length is mm, the force is in Newton, but the mass is in ton.
Okay.
It's not in kg. So the density will be ton per mm cube.
Okay.
So the TPU density is in gram per centimeter cube, right?
Yeah.
Gram per centimeter cube. So I want to make gram per centimeter cube to ton per.
So you have to change the
Yeah.
unit.
So you see gram per centimeter cube to ton per mm cube is 1.23, and I convert this, it becomes 1.23 e to the power minus 9.
Yeah.
Right? So I will put this here, e minus 9. Here.
Okay.
This way.
Let me take a picture.
Yeah.
Okay. Property.
Yes. Usually we just keep the uniform density here. We don't have to change anything. So the density is set. Now we need to set up the mechanical property. For TPU, because it's a hyperelastic material.
Yeah.
So Sam, what should we select?
Yes, and hyper.
Hyper what?
Elastic.
Hyperelastic, right?
Yes.
Okay.
So we say go to elasticity.
It's not hyper. Oh, it's hyper.
Hyperelastic, yeah. We go to hyperelastic because it has a rubber-like property. So since since we don't have any anisotropic property in this, we always select the isotropic because take the material as isotropic.
Yeah.
Okay. Now we have the test data.
Hyper elastic.
Eric, can you give me my bottle?
You want your bottle? Hey. need to type it. Okay, so chopping.
Okay, you're all set.
Yeah.
Now, because we do the experimental test, so we have the test data. We click on test data, go to actual test data. I click on this, and now you see it asks the nominal stress and the strain.
Yeah.
So this is Sam's average stress and strain data. You already put this file in the computer.
Okay.
So I just copy the stress and the strain here from here.
Yeah.
Stress and the strain,
Yeah.
and paste it here.
Okay. Okay. Where do you open this window?
Which window?
This.
This one is here. Test data.
Test
Uniaxial test data.
Uniaxial. Okay. So you use the okay. You use the impact data of it, stress, strain. Okay.
不是这个是做拉伸实验的。
Oh, it's the material property. So you use the okay. I know. You use the tensile test.
Tensile test data. So stress versus strain. Do not take strain percentage. Take strain. Okay.
Strain.
I press OK. Now, here you see it says the strain energy potential. Okay. Let me open. You see there are many kinds of hyperelastic material models. Okay. And we just you see this one, the Abaqus stocks. If you don't remember or don't understand anything, you can always come to Abaqus documentation to understand everything. So you can see here. Yeah, Sam, I told you about the new, right? You see the new. If it goes increasing too much, you see the K naught by mu, this one is the bulk modulus, increases way high. You see the shear modulus here.
So we need to set
0.48, yeah, 4849, anything you can set. So you can see that the strain energy potential, these are the different mechanical equation.
Yeah.
I did not show you this Sam yesterday. You can see there are many. This one Aruda Boys, it has different mathematical equation. Marlowe have different mathematical equation. This is different mathematical equation. This is different. This is Ogden the one. So there are many kinds of mathematical equation. But which one is for our material that we need to identify?
Yeah.
So let's look at how we can go about doing that. I've just uploaded the test data, but I don't know which one is what. I just press OK, and then I click here, and then this TPU, I will just click on evaluate.
Okay.
Yeah. So when I click on evaluate, because I've already set the hyperelastic parameter, so it will give me the different strain rate potentials like this. So usually I will just take polynomial. I will take Ogden 1, 2, 3. Maybe this one if I want to take a reduced polynomial 1, 2, and 3 up to this.
So it's
usually
this represent different
equation. Yeah.
Okay.
And the more the number of n, the more complex is the equation.
Okay. So it will more precisely describe the TPUs.
It does. It not necessarily it will precisely describe, but it becomes more complex because you see it's a summation over n.
Yeah.
That means it will have 1, 2, 3.
Oh yeah.
So if there are two
the
terms
equation,
like this,
yeah,
it becomes more term. So the more term is the equation, the more complex it becomes, and it's difficult to match.
So you press the.
So usually, from my experience, I just take up to 3 order.
Okay.
More than that is always unstable. So let's just check how it is. I press OK, and we get the analysis report.
So we have to wait for its report.
Yeah, you see this as a report. Okay. material parameters and stability limit information. So this is our main curve. You see, the red is our test data, and the other is the fitting data. So let's just zoom this and see. So you see many of the curve, they just match with our curve also.
Yeah.
Okay, but which one is the closest? Let's investigate. So the first thing you can investigate is you can just see here which one is stable for all. So polynomial 1 is stable for all strains. Stable for all strains means you see there are different tests:
Yeah.
uniaxial, biaxial, planar, volumetric.
Yeah.
So if your material mechanical properties are stable for all these tests,
Yeah.
then it's stable for doing the simulation.
Yeah.
So you see this one is stable. You go to polynomial n2, but you see there's unstable at this strain, unstable at nominal strain larger than 0.22. So in this sum of the tests, they are unstable. So we're not going to use this material model.
Yeah.
So n equals to 2 is not needed. You see the complexity increase, the stability decrease.
Okay.
Let's look at Ogden 1. Ogden 1 also match everything.
Okay.
Ogden 2 is stable for all. Go to Ogden 3. No, it's not stable.
Okay.
There is some problem.
So you just choose some model for it, and you choose the stable one.
Yeah,
for
stability
it.
state.
Okay.
So let me just go here. Now this is also stable.
Yeah.
This is also stable. And this is also stable. Okay. So in our scene, we found that n equal to 2 and O equal to 3 is not stable.
Yeah.
So let's go back here and remove those things. And we go back up to do again. N equals to 3 is gone. P is equal to 2 is gone. And then press OK.
So just choose the stable.
Yeah. So you see these are all the stable ones, right?
Yeah.
But which one is the best? Let's investigate. Now we have our curve. Initially you see this road region is very important, because this is how from here your material starts to stretch a lot.
Stretch. Yeah.
So let's zoom in here and see which line is the closest to the red.
Okay.
So we see that this blue line is the most closest in this region. The blue line here. And the blue line is what?
Ogden N2.
Ogden N2, right? So the blue line is the Ogden N2, and it is the most closest to our curve. So we going to select the Ogden N2 model.
Okay. Ogden N2.
Yeah. So now we can open this, go to uniaxial test data. Here we select Ogden,
Okay.
and then the potential order is 2.
Oh,
Because N2.
When did you go to this page? AB.
Yeah, you can. Okay. You just come here,
Okay.
because we saw the evaluation.
Yeah.
Even if you want to see, go to results,
Okay.
and yeah, this is your data. Okay.
Yeah.
But we have the data now. We know that Ogden N2 is very close to what our curve is.
That's true.
So we go back here, double click,
On double click. Okay.
because we haven't selected anything here.
Yeah.
Select Ogden, then 2.
Okay.
Strain potential order is 2. Now Poisson's ratio I will select as 0.49 or 48, anything. Never select 0.45, because if you select 0.45 here, the denominator becomes infinity.
Oh, you
This
will have the other defined.
Yeah. This one becomes very large.
Okay.
So this becomes infinity, and your solver will never solve. It will just stop. That's why it's better to select 0.48 or
Okay.
0.49. It's okay. Now once we set up everything, we just press OK. Your material property is set for TPU. Now because we have the impactor also, so we make another one which is metal for the impactor. So this will become stainless steel. I just write SS.
Okay.
So usually the density of stainless steel is, you remember,
7.4.
2.
what did he say?
7.2.
It's very close to 7.8. 7.8 to 8.
Okay.
So you can just select 8.
Because I used these before, so I
yeah.
know the because I do a lot of stainless.
Yeah, so it's very close to that.
Yeah.
So I just write 8e minus 9. So this is your tons per mm cube. Here. Tons per mm
Okay.
cube. So you just always remember the units. If your units are gone, your results are totally gone.
Yeah.
So this is your density. And then I select the elasticity because I just need the elastic property. It is not going to deform.
Yeah.
So what's the Young's modulus?
Infinite.
Young's modulus, steel.
I don't know. Actually, I'm not sure. What's modulus? Okay, we can ask Google.
Yeah, Google's always there.
Oh, gigapart.
It's very close to 20,000.
20,000.
Yeah. Where's the Young's modulus? Yeah, you see the Young's modulus is around 190 GPa, but we have to make it as MPa. So there will be 3 more zeros from here because the unit,
Yeah.
it needs to be megapascal.
Megapascal.
So I just select 2 e to the power 5 because it will become around 20,000.
Yeah.
Okay. So I just select this one. Gigapascal, right? 200,000. Yeah, e to the power 5, correct. And then Poisson's ratio is somewhere around 0.3.
Okay.
Once we just set this, press OK. So all the material properties are set now. Now we need to assign the material to the component.